All right, Algebra 2 students, we're going to wrap up this linear programming thing we were doing here. Let me find my paper. There it is. Okay, let's download this sucker. Pull it up this way so that you can see it better. Okay, so this sums up, well, I've done linear programming. You did that with the lab staff and the military rations, and you did it with pecan prizes, problem, and what was the other one? Farm figures. So in all of those, this is puts some terminology and sums up the process that you use. In linear programming, it says, what do you have? You have a feasible region. Do you know this word feasible? F-E-A-S-I-B-L-E. We don't use that word really often. Feasible, you might hear somebody say, well, that's just not feasible. That means it's not possible. So this feasible region, the part that's shaded for all of those inequalities, gives you all of the possibilities, the possible solutions. Now, we focused on finding the minimum and maximum, but do you understand that every point in the shaded part, every single ordered pair we could make inside that shaded part would be a possibility? So it's formed by graphing a system of inequalities. Remember, systems means more than one inequality, more than one variable. Under these restrictions, you must maximize or minimize some other function like cost or time or profit or some feature like that. So how do you do it? You use the vertices, that's the plural of the word vertex, of the region. Now, in these other examples on here, what we're going to do is graph these, and we're going to practice finding that feasible region and maximizing or minimizing some function. All right. Let's move this up a little bit. Okay, problem number 1 says y is less than or equal to negative 2x plus 4, y is less than or equal to x plus 7, x plus 3y is greater than or equal to negative 3. Find the maximum and minimum values for c using c equals 8x plus 11y. All right, let's look at this. That first inequality says y is less than or equal to negative 2x plus 4. Y-intercept is 4. Slope is negative 2, down 2 and right 1. Up 2 and left 1. And I know that's a solid line because the symbol has a line through it. And since it's less than, we would shade below. I'm just going to draw arrows instead of scribbling all through that right now. The next function says, the next inequality says, y is less than or equal to x plus 7. Y-intercept is 7. Slope is 1. Now, I could go up 1 and right 1, or I can go down 1 and left 1. Down 1 and left, down 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 and left. And this is also a solid line. And this one I'm shading below. You see in a pattern. Now we would shade below this one. And then this other one is x plus 3y is greater than or equal to negative 3. If I want to get that y by itself, well, that didn't work, did it? We have 3y greater than or equal to negative x minus 3. Divide everything by 3. You have y is greater than or equal to negative 1/3 x minus 1, which makes the y-intercept negative 1. And the slope is down 1 and right 3, down 1, right 3, or up 1. left 3, up 1, left 3. That is a solid line. Just missed that point. And this one we're shading above. So you notice that this feasible region in this particular problem looks like a triangle. Okay. That feasible region is the part that's shaded for all three. We got to find some vertices here. This one is 2, 6. No, that's 1, 6. So then we would plug it in here. Cost equals 8 times 1 plus 11 times 6. 8 times 1 is 8. 11 times 6 is 66. 66 plus 8, 74. Okay. That's this vertex. Now, what about this one is 1, 2, 3, negative 2. That's this one. 8 times 3 plus 11 times negative 2. 8 times 3 is 24. 11 times negative 2 is negative 22. So leave us 2. This other one is here, and that's negative 5, 1. What are we doing? We're taking the ordered pairs from the vertices and plugging them into this function or this equation. 8 times negative 5 plus 11 times 1. That's negative 40 plus 11, 29. Be negative 29. So then you would find your negative and your minimum and your maximum. So okay, what did we do? We graphed the inequalities, we shaded them, and then we used the vertices or the corners of the feasible region. I'm going to see if I can find the key to that. Just a second. Let's get rid of that so you can see a little neater picture. I'm going to go back. And this magical little search. I want to put my stylus in my mouth. That would not be good. Okay, my math was off. I thought one of my points was probably off. I didn't recognize those numbers. There's your vocabulary at the top. Feasible region, system of inequalities, maximum, minimize. See, even I couldn't read my graph because it was messy. Okay. So look, this point was negative 6, 1. That's this point right here. And they've taken that negative 6, 1 and plugged it into this equation and got negative 37. Then they took negative 1, 6, which is this point. Okay, I did 66 plus 8 instead of 66 minus 8. That's where my math was off. Okay, see where they plugged that in? And then they took this vertex that's 3, negative 2, and they plugged the x part of that coordinate in for x, the y part for y. Your minimum is negative 37, and your maximum is 58. And I have to plug this in or we're going to die. Hang on just a minute. There we go. We live. Okay. Now let's go back to this paper. Okay. So what are we saying? What is the important part here? Linear programming takes a system of inequalities like this, and it graphs them, and it takes the shaded region for all three. It's called the feasible region, formed by graphing a system of inequalities. You can use this to maximize or minimize some function like cost or time. So be useful in business to know what your profit's going to be, that kind of thing. Use the vertices of the region. Vertices is plural of vertex, which is the corners. Okay, let's look at the next one. All right, you have y is less than or equal to negative 2x plus 4. What's your y-intercept there? The y-intercept is 4. This is the same thing we did in those other problems. We used Desmos to graph it, and you can do that. But your y-intercept is 4, your slope is negative 2. So that's this blue line right here. Then y is greater than or equal to negative 1/2 x minus 2. That's the red line. And this x is greater than or equal to negative 2. That's a vertical line, so that's this purple one. So now we're going to take this corner, this corner, this corner. Those are called the vertices. So the vertex negative 2, 8 is this one up here. Plug them into this equation. Take the vertex negative 2, negative 1. That's this one. Plug it into that equation. Take this one, 4, negative 4, and plug it into that equation. Use these numbers then to find your minimum and your maximum. Okay, this is what linear programming is. This is what you used in the military rations problem and all those others. Okay, let's go. Here are 4 more inequalities. Graph them by Desmos. Where did it go? There it is. I want the key. Where did the key go? Sometimes I think my computer has a ghost. Okay, we looked at that one. Sometimes, a lot of them, your feasible region looks like a triangle if you have 3. Look at this one. It's kind of like the lab staff one, a pecan process one. You've got 4. Notice what they've done. They've graphed those inequalities. They've shaded. This is the part that's shaded for all 4. What have they done? Then they went and found the vertices. This one, this one, this one, this one. It's the boundaries or the corners of that feasible region. Here's those vertices. 2, 4 is this one. 3, 6 is this one. 12, 0 is this one. And what's the other one? 6, 0 is this one. Then take those, each of those points has an x and a y, plug them into this equation. Use these numbers to find your minimum and maximum. That's what linear programming is, folks. It's taking that system of inequalities. Think about your word problem. Think about the military one. Where did those inequalities come from? They came from the restrictions or the guidelines for that situation. You remember in the military rations problem that each soldier could have no more than 12 servings. That's where we got one inequality. Each soldier had to have at least 2,015 calories. That's where we got one inequality. Each soldier had to have at least 300 grams of carbohydrates. That's where we got one inequality. And what was the other one? That was it. There was the calories, the carbohydrates, and the number of servings. That's where we got our 3 inequalities. With the lab staff problem, it came from the number of scientists and assistants could be up to 30. It came from you must have at least 4 scientists. It came from the number of assistants had to be at least half the number of scientists. And it came from the square footage requirement. So those inequalities come from problem situations and guidelines. They're called constraints. All right, let's see what else we got. Now, I wanted you to see this one because look what happens when we graph this one. Look at all these inequalities, 1, 2, 3, 4, 5. When you graph it, this feasible region, does it stop? No, it keeps going. You see, it keeps going, would keep going off of the graph. There's no boundary on the outside. So the vertices that they used were 0, 12, which is here, and 2, 6, which is here, and 4, 3, which is 1, 2, 3, right here. Sometimes people miss that one, and 10, 0, which is here. See, there's no vertex up here or to the top or to the right. So they took each one of those and plugged them into this equation. And notice it says find the minimum value, because is it possible to find a maximum? It's not, because we don't have a boundary. If we made a bigger graph, it would still be shaded. All right, that's linear programming. What's a feasible region? What is a vertex? And how do you find the minimum and maximum? Those are things you can answer about linear programming.